Okay, well, it's my pleasure to welcome Megan Donahue to give our talk today. Megan got her undergraduate degree at MIT in physics, and she worked with Claude Canizares and Tom Markert, I believe, if I remember correctly. After leaving MIT, I won't stick years in just to be kind, but after leaving MIT, she went on to the University of Colorado and got her PhD with John Stocky, looking at galaxy clusters, discovering galaxy clusters using H-alpha emission and various other things. After getting her PhD, she went on to do a postdoctoral fellow at Carnegie Institution at Carnegie Observatories in Pasadena, where she spent a few years. And I believe at that time her husband and science partner, Mark Voigt, was a postdoc, I think a Hubble fellow at Caltech, if I recall correctly. And so following that, they went off to the Space Telescope Science Institute, where they were faculty members for several years. And then they both got offers to go to Michigan State as faculty, and they've been there since I think the early 2000s, mid 2000s or so.
Mm-hmm.
And but so Megan is well known for her studies of galaxy clusters and galaxies in essentially all bands, from X-ray to H-alpha to optical observations. She is a key member of several space telescope projects to study galaxy clusters, and has done seminal work in all of these areas, understanding how thermal instability and in atmospheres occurs, star formation, cooling, much of the things that certainly I've come to know and love. Most notably, recently Megan sorry, I've got some background noise, just stepped down as, or just finished her term as the president of the American Astronomical Society. And she's, had a big impact on the society doing with several initiatives, including buying up the fledgling, not fledgling, but I think dying Sky and Telescope, and getting that going again. And I'm not sure all the details of that. We can talk about it later, but I thought that was a really cool initiative. And also, supporting women in astronomy and trying to root out a lot of the issues with that, gender imbalance as well. And so these are really huge initiatives that she spearheaded with the society and has been very successful. And now she's back to doing, I think, what you have always known and loved, which is doing research again and teaching. And so with that, Megan is going to talk to us about.
Oops. I think we
Someone cut him off.
That's right. Someone cut him off. All right, get him out of here.
That wasn't intentional. I think you should start now, Megan.
I'll just start. Yeah. So I'm going to talk about a problem that is bigger than I could ever cover in 3 hours, much less 50 minutes. So you'll forgive me if I focus on a couple things that I'd like to talk to you about today. But I will start from a broad perspective, in the sense that, when we look at the ingredients of the universe in terms of the equivalent energy densities, dark energy, of course, dominates. You have 24% of it being dark matter. A trace amount of the matter is gas, and even a smaller trace is stars. And inside a galaxy halo, the matter fractions is mostly dark matter. So one thing to keep in mind when we're talking about galaxies and clusters is that most of the matter holding the system together is dark matter. And then there's a trace amount of gas, and then even a tinier trace amount of stars. And we think this dark matter particle is a non-interacting particle except for gravity. So weakly interacting massive particle is the most common broad category of a particle for candidate for dark matter. And it can be modeled pretty simply, ironically, just through by modeling gravitational processes. But because baryon physics can include things like shocks and cooling and so forth, it's much richer than the physics of this dark matter. More equations are needed to follow it. And so galaxies in the centers of clusters of galaxies are not just simple, scaled down versions of each other. There's a lot more going on that is needed to explain the distribution of baryons in these dark matter halos and also the distribution of stars. So to orient you a little bit into some of our mental pictures that we have of galaxies and clusters of galaxies, let me just show you this sequence of animations I like to show to a general audience, showing where the stars are in our own galaxy. So this is an all-sky picture that highlights the Milky Way galaxy running through the center of this all-sky picture. But the stars really are a tiny bit of the total gas and dark matter, and where it sits is also very different. The gas and dark matter surround the galaxy in a vast halo. So that's our concept of this halo, and then the stars are just this disk or distribution in the center. Most of the baryons are not in the stars, they're in this distributed gas. And indeed, most of the heavy elements aren't in the stars anymore. The stars make the heavy elements, but dying stars release them to the gas phase. And so most of the metals currently in the universe are also not in stars, they are in the gas. So here's a cartoon picture of the galaxy edge on, and it's surrounded here by the circumgalactic medium, which has a characteristic radius. And this radius will kind of come up in the talk once in a while, so I want to define it. This radius is the radius inside which the average mass density is 200 times the critical density of the universe. It can be written in terms of the halo mass and the an expression that describes the evolution of the Hubble constant over time. So this contrast radius gives us a standard radius out to which we measure or hope to measure the halo masses of things. So we need to define that radius in order to define masses of extended things. So that's why I wanted to show you that cartoon. So in galaxy formation, there's a couple of issues. One of the things that we've known for a while, but Sloan Digital Sky survey, with its vast numbers of measurements for galaxies and including the colors and spectra, have shown that galaxy colors and star formation states of galaxies are strongly bimodal, in the sense that the star formation rate and the stellar mass have two sort of centers. One is centered on these galaxies that have very little star formation. They're sometimes called quenched galaxies. And then there are these galaxies where star formation is going on. And the numbers seem to peak. There's a population of quenched galaxies and a population of star forming galaxies. And then there's this, what they call green valley galaxies, which I'm not going to talk about. But any picture we have for how baryons evolve in dark matter halos have to explain why some galaxies are quenched and some galaxies are star forming. And there appears to be a very subtle distinction in mass between those two systems. I hope to be able to show you a slide that shows you that it's more strongly bimodal if you plot these galaxies in terms of velocity dispersion. I may or may not get to that though. The other kind of puzzle is in this context of hierarchical structure formation is that massive galaxies apparently stop making stars sooner in the history of the universe than less massive galaxies. This is a empirical outcome that's sometimes called downsizing. I don't think that's the greatest name for it, but it is what it is. And it in a way kind of flies in the face of, a picture of structure formation where small things merge and make the bigger things. And that's a structure formation picture that's following strictly the processes of gravitational accretion in an expanding universe, but is not taking into account, of course, the baryonic physics. So it's baryonic physics that somehow is going to explain why massive galaxies form their stars first and then boom, stop forming them, while lower mass galaxies continue to make stars. So this is a plot from Baruzzi's, I believe it's based on his PhD theses and work thereafter, where he's plotting halo mass versus stellar mass. They infer halo mass through a process called abundance matching, which I won't get into here, but it was by analyzing all these galaxies from the Sloan Digital Sky Survey, they were able to infer this pattern of halo mass versus stellar mass as a function of redshift. So as you move left to right in this diagram, you're going from redshift 0.1 to redshift 8, so relatively recent in time to the distant past. And you see that the peak in the star formation in the stellar mass over the halo mass moves to the left with time. And so one of the inferences from this work, this is from his 2019 SDSS data, is a plot that shows that the galaxy's efficiency at converting gas into stars has a special peak when its mass increases to be about the mass of a Milky Way galaxy. So a galaxy increases in mass over time, and for some reason, when a galaxy's mass is about the mass of the Milky Way, it is at its peak efficiency at converting gas into stars. And as it goes to higher mass, it decreases in efficiency. And when it was at lower mass, it was at a lower efficiency. Simulations, at least the early simulations of baryons inside of dark matter halos had an interesting failure mode. What they found is that when they attempted to model the formation of stars along with the gravitational interactions of gas and dark matter, they would get something that's been called the overcooling problem, where gas halos around massive galaxies cool and condense and make many more stars than are observed. And so even though they recognized fairly early on that they had to include some of the feedback from star formation, and the feedback from star formation includes things like supernova explosions, winds from stars. Stars clearly affect their environment as they form, because the most massive stars die almost immediately within about 10 million years of forming, which is almost instantaneous in cosmic times. When they die, they blow up, and when they blow up, they inject energy into their surroundings. And you really have to take this into account to properly model how efficiently gas can be converted into stars. And even taking this into account, these early models could not replicate the stellar fraction of stars in the most massive galaxies. They would overproduce the stars. So some kind of feedback is needed, and the main culprit that emerged was possibly the AGN, this supermassive black hole that seems to sit in the centers of most, if not all, massive galaxies. And the early, I would say the early approach was very optimistic. It's like, well, if you set off a bomb in the center, that would, solve all our problems. So of course, AGN feedback is going to be really the solution, but it turned out to be a much harder process to implement than initially envisioned. And so some of the scenarios for AGN feedback can be divided into roughly two classes of solutions. One is ejection, which would launch, eject the gas out into the intergalactic medium, and that ejection can be driven by supernova feedback. It could also be driven by AGN. There is a parameter that the models use to a single parameter that is the efficiency of how much of the supernova energy, which has to be there, because if there are stars, there were supernova, how much of that energy can be distributed into the surrounding gas. And that is characterized by a factor called eta sub E, which you'll see in a couple plots later. So that's why I'm defining it here. And then there's a generic sort of maintenance mode where if you have the gas that's surrounding the galaxy, and if you could prevent that gas from falling into the galaxy and make it very, very slow for gas to cool and condense onto the galaxy, that's kind of generically called what's known as maintenance mode or preventative feedback. And in that sense, the rate of accretion onto the galaxy, or at least onto the place where the stars are forming, is very, very inefficient. So if you can keep that gas puffy and hot, then it's going to be slow to cool and condense. So there's sort of these two classes of models that simulations consider when they're thinking about feedback generically. Oops. And from the stellar point of view, galactic winds can mostly solve this problem for low mass galaxies. Now, there's probably still some details that need to be worked out, but for low mass galaxies, galactic winds, in other words, the aggregate of all the supernova explosions and winds from high mass stars and so forth, can work to regulate those galaxies and solve the overproduction of stars problem. At higher masses, there's a couple things that change that are sort of important to track. As the gas falls into those higher mass galaxies, the accretion shocks get stronger. And so accretion shocks alone can heat and warm the gas to high temperatures. This leads to longer cooling time, because gas with longer cooling times and lower densities leads to gas, at least some of the gas in these higher mass systems, which can't cool with inside of a Hubble time. A Hubble time is the equivalent of the age of the universe, and it's roughly proportional to the inverse of the Hubble constant. So 1 over h naught is approximately a Hubble time. And the other thing that changes at higher halo masses is that the galaxy-galaxy interactions that happen in a dark matter halo of higher mass occurs at higher speed, and mergers become less likely. So galaxies don't just naturally pile up into one giant central galaxy. You tend to get a central galaxy with a lot of satellite galaxies in these higher mass halos. But even with this assistance, the feedback from stars is not sufficient to quench these massive central galaxies in these simulations. So we know that supermassive black holes exist in almost every massive galaxy, because of, and that the mass of the black hole is correlated with the stellar mass of the bulge. And so that leads to this the inference that AGN are the likely culprit for regulating the baryons in the most massive systems. So here's a plot I'd like to share with you. This is from a review that is currently under review at the Reviews of Modern Physics. And it's a plot that's based on the data from Baruzzi. So you saw the data before, that's these Z of 2, 1, and 0 lines. And what's imprinted on this plot also is on the left are lines which give the minimum stellar fraction, that's what's plotted over here, the stellar fraction of the baryons, and the minimum amounts of stars required to eject gas from radius r. So if we assume 100, okay, let me step back. On the left-hand side, we're modeling an ejection and calculating what the stellar fraction would be if the gas is ejected from various radii. So if the line is above the curves, that means the stellar fraction is higher than what the data show us it to be. So if you have only supernova feedback, but operating at 100% efficiency, and it has to eject the gas from a radius of 0, you see that it fails to reproduce the stellar fractions for all mass scales. But of course, not all the gas is sitting at r equals 0. So if it's sitting at somewhere close to the scale radius of an NFW profile, that's going to be, it's going to be more feasible for supernova ejection to work for the lowest mass galaxies. But notice it still has to be basically 100% efficient, which is pretty unlikely. And then if it only has to eject the gas from 5 scale radii, it's more than sufficient to get the stellar fractions that you see at star-forming galaxies, especially for redshift 0 star-forming galaxies. But notice all of these models fail to reproduce the stellar fractions that are observed for higher mass halo systems. On the right, this is showing the calculation for, instead of an ejection, but a lifting of the circumgalactic medium. A lifting of the circumgalactic medium doesn't remove the circumgalactic medium, but makes it, if you lift it by a factor of 2, you make it 8 times less dense, and that will also slow down the cooling rate. And here, the efficiencies don't have to be 100% to easily explain the star-forming galaxies. But even lifting, although it's easier to do, fails for the highest mass systems, even if the efficiency rate is as high as 100%. So looking at the gas halos in the X-rays is a really effective way for testing some of our ideas about this. And the X-rays have a similar sort of issue that was recognized in the early days of X-ray astronomy of an analogous overcooling problem. And I'm going to go through that kind of quickly here. So on the left, we have a Hubble Space Telescope image of a cluster of galaxies, and you can see the arcs of the gravitationally lensed arcs of background galaxies. And then on the right, you see the Chandra image of the same galaxy. So, and then this is the two images superimposed. So brightest cluster galaxies have an interesting bimodal pattern in and of themselves. They are largely quenched galaxies by an optical galaxy definition of quenching, in the sense that they're not making a lot of their stars right now, but they're there is definitely a bimodality in the sense that there are some brightest cluster galaxies that are forming stars fairly rapidly, even though it's not rapidly for their stellar mass, it's rapidly in an absolute sense. Some of the highest star formation rates in the local universe are found in brightest cluster galaxies. It's just that even that at that rate, 100 or more solar masses per year is not enough to be assembling the galaxy at this point. So technically they're quenched, but in an absolute sense, they're a starburst galaxy that's surrounded by a giant mass of old stars. And then a lot of them look like this more traditional red and dead distribution of galaxies, of stars. So brightest cluster galaxies are bimodal as well. When we look at things in the X-rays, we can make several types of observations from X-ray data. X-ray data allow us to measure surface brightnesses. And from the surface brightness profile, this is the surface brightness as a function of radius in the top plot for the coma cluster, which I just pulled out as an example of X-ray data. You can infer the electron density from the surface brightness profile. And from the same data, we can compile X-ray spectra, because these data are event files. In the event, each event has an energy and a location on the sky. So we can either make an X-ray map or we can make a spectrum. And the spectra allow us to infer the temperature and in some cases the abundance, the iron abundance of the gas, the hot gas. So in equilibrium, this hot gas is roughly is driven by the circular velocity, and so it represents the temperature of essentially the temperature of the gravitational potential. Since the X-ray data allow us to measure temperature and density, and if we have resolution, we can measure a temperature gradient or a temperature map or a density gradient or a line of sight density profile. We can convert to gas entropy and pressure using combinations of the temperature and density information. And these are the X-ray observables that allow for us to probe the thermodynamic state of the gas. And in this gravitational potential, a stable entropy and pressure gradient will increase from the inside out. You might have cooling, but the cooling of an X-ray gas doesn't really change it all that much in temperature, because remember, its temperature is really reflecting where it is in the gravitational potential. But there is a cooling time we can define, which is the time it would take for the gas to completely cool. When it's defined as 3/2 P over the pressure divided by the luminosity density, this is the inverse entropy time gradient when the cooling is purely radiative. So this 3/2, which could be 5/2, depending on how you define this time. The reason that in our papers we use 3/2 is because of this convenient relationship between the cooling time and the time it takes for the gas entropy to change. Okay, so I usually wind up spending too much time trying to explain entropy and pressure, but let me just show you this pressure entropy diagram and help you navigate it a little bit. So pressure is being plotted on the x-axis and entropy is being plotted on the y-axis. Entropy as being defined in the previous slide to be temperature divided by the density to the 2/3 power. And you can see the lines of constant cooling time going from the left-hand side of the diagram to the right-hand side of the diagram. The wiggles on that curve are determined by the cooling function, which is somewhat sensitive to the abundance, the iron abundance or the heavy element abundance of the gas. These particular lines correspond to gas in solar, with the solar abundance, but they're not too incredibly different for gas at 1/10 of a solar abundance. So for illustrative purposes, I'm showing the results for these curves correspond to a solar metallicity gas. Lines of constant temperature go diagonally down this plot. Lines of constant density move from the lower left to the upper right. And within this context, I can plot the density profiles for several different kinds of systems. A couple of clusters of galaxies sit over here. This is NGC 1275, or the Perseus cluster, and its point at 100 kiloparsecs and its point at 10 kiloparsecs are here. Our next door neighbor, M87 in the Virgo cluster, has its profile points also plotted here: 100 kiloparsecs, 10, 1.1 kiloparsecs. An elliptical galaxy, NGC 4472, is plotted. It's cooler, but you can see that its entropy at similar radii is similar to the entropies of the clusters. And over here on the left, I have a plot of the appropriate values for the gas halo around the Milky Way. And one of the things that I find remarkable about this plot is that from the Milky Way out to the Perseus cluster, the cooling times and specific entropies are similar at similar radii, but the pressures are an order of magnitude different. And the second point is that the cooling times inside of about 10 kiloparsecs are much, much less than a gig year, and even shorter at a kiloparsec, a few 10 million years. And early X-ray astronomers instantly recognized this as that a short cooling time must imply some kind of longer term regulation mechanism. Spitzer in 1956 incredibly inferred this from the gas pressures that would be required to confine circumgalactic gas clouds that were just being reported and discovered in absorption line spectroscopy in the late 50s. And so Spitzer happens to be my academic grandfather through my other thesis advisor, Mike Scholl. And he just turns out to be an amazingly brilliant guy. He also
Can I just ask a question about this plot? This is from another Spitzer grandchild, great grandchild actually. But the slopes, I noticed that for example, the Milky Way, the temperature looks the same from small scale to large scale, whereas for example, NGC 1275, there's quite a difference. It's quite a bit hotter at the large scale. Does that correlate with cluster? Like the galaxy clusters are hotter on the large scale?
Some clusters have cooler centers. And you know, even in M87, the center is a little cooler than the outskirts. There's a bit of a temperature gradient. The temperature gradient, once you get outside of the central core, is usually not very strong, even in clusters.
Okay, yeah, it looks like about a factor of 3 for M87 between the innermost and outermost part in temperature. And
yeah.
So there is.
So the temperature gradient is almost completely due to what you'd expect from the gravitational potential gradient.
Okay, thanks.
Right. Not due to cooling or anything like that. Yeah. And then, you know, some guy took advantage of early observations from the amazing Chandra Observatory, Brian there, to show that this spectacular new view of the universe, Chandra had this incredibly high resolution, allowed us to show that the AGN indeed were doing something in the centers of clusters of galaxies. And it was easier to see in clusters because the clusters are brighter in the X-rays, the pressures are higher, and so the energy from an AGN is more prominently captured and imprinted in these vast cavities of excavated regions that are filled with radioplasma. So I'm sure you've heard some really great talks from Brian on this. This is really incredible stuff. Just a little aside, when I was a graduate student, maybe this is true for Brian as well, I was told, well, maybe you'll do your thesis with Chandra, or AXAF as it was called. I think I can say that I would have been stunned to have known in advance of my career that a lot of my career would be fueled by observations from Chandra. So a long-lived observatory that's still plugging away right now. The AGN feedback scenarios predate Chandra. Some of the first people to propose them with Binney and Tabor in these papers from 1993 and 1995 in order to solve this cooling flow puzzle. The fact that there were short cooling times in the centers of these clusters of galaxies, but the Chandra and radio observations from Brian and others gave just spectacularly beautiful evidence that no question the AGN was part of the solution to this so-called cooling flow problem. Very relatively recently, about 5 years ago, the Japanese space agency, together with contributions from NASA, launched a high resolution, high energy resolution a spectrometer. Finally, those of you in the know that there have been multiple attempts to launch high resolution X-ray spectrometers into space, and they've all ended rather poorly. This one lasted long enough to get a glimpse of the Perseus cluster, which and these data have launched many papers, and where they were able to detect and resolve the iron Lyman alpha line from hydrogen-like iron and get a velocity dispersion, which limits the overall turbulence in the gas to 164 plus or minus 10 kilometers per second. That led to the inference that turbulence is not providing much of the pressure support in the gas, and the gas is, despite its surface brightness appearance here in this edge enhanced picture produced by Jeremy Sanders, the turbulence is not what's supporting the gas. It's supported primarily by thermal pressure. So there is, well, anyway, so that's really quite interesting. Perhaps not super surprising, because the pressure of the gas in a cluster of galaxies reliably also predicts its masses as its gravitational mass as estimated from other sources of information, including gravitational lensing. But it is interesting because turbulence is probably one of the ways that that energy is transported in the gas. And so energy transport is a real important puzzle that still isn't quite solved by just saying, okay, looks like the AGN works, looks like the AGN is injecting enough energy to counteract the cooling, but how is it transported in the gas? Turbulence seems to be one of the key mechanisms, and that is something we'd like to better measure and explore. So what do we need to do? I'm going to go through it, a little commercial. what do we need is high resolution spatial and high energy resolution. And the mission that was proposed to the Astro 2020 survey for the US contemplation of the priorities for NASA in the next decade is called LINKS. And so let me show you some glamour shots of the LINKS concept. So this is the logo, and I have a personal connection to this logo because I commissioned it. My sister-in-law is a graphic artist, and she told me one summer, she said, you know what, I'm really good at logos. You guys need a logo? And I said, I need a logo. And you know, through various circumstances, she designed us a logo. So LINKS has a logo, it's amazing. It also has 3 science drivers. It will have high resolution, so it will be able to see black holes out to the birth of the earliest black holes in the universe. It will also be able to study the energetic side of stellar evolution. But where I'm really interested in LINKS is on this side of the 3 key projects, and that is how AGN and hot gas work together to drive galaxy evolution in general. There's a lot of connections to be made there with non-traditional X-ray astronomy. And so here is a simulation of the wide field X-ray imager. This is 100 kiloseconds at between 1/2 and 2 keV. And there is a redshift 3.27 galaxy group with a mass of about 3 × 10⁻13. So it shows up as a smudge on the frame. So a single wide field image will have many of these clusters and groups in them. They will show active galactic nuclei. And for comparison, here is, you know, the HST counterpart to this galaxy group. This is what XMM would see, and then this is what 100 kiloseconds. I'm sorry, this is a redshift 2 cluster. 100 kiloseconds on a redshift 2 cluster looks like this in XMM and would look like this with the high definition X-ray imager. So notice there's a couple different nuclei, and there's lots of fun things you can see and distinguish background or foreground AGN from the emission from the cluster. So every 100 kilosecond HDXI exposure would be deeper than the 7 megasecond Chandra deep field south. So LINKS clearly qualifies as an upgrade from Chandra, even though its spatial resolution is not a big jump up. Its collecting area and the wide field field of view is much, much bigger. So its data rate and its depth will be much, much faster. So, sorry. So now I'm showing a simulation, and this is HDXI footprint. You would see 7,000 sources in a relatively blank part of the sky. And then zooming out to the large scale structure, this is a picture, this is a simulation of large scale structure at the megaparsec scale with the HDXI footprints plotted for scale. This is a simulated cluster at the center, which is, you know, this is what we'd be able to study with Chandra XMM. But this is a redshift 0.0125 a cluster of galaxies with the attendant large scale structure filamentary gas falling in at very, very large scales. So the legacy field, which is, just a hypothetical a key project for links, is 10 megaseconds in 10 square degrees, and it would be able to detect the filamentary baryonic gas at megaparsec scales, which is really, really incredible. So if you want more information about links, you can go to the website www.hiddencosmos.org, and I'm going to give credit for this slide to Grant Tremblay, who put together these slide sets for the promotion of the new Great Observatories idea. And I could talk more about that after the talk if you'd like. So let me summarize some of the clues we have about AGN feedback from clusters of galaxies. The clues, some of the clues come from the entropy profiles. There is a baseline cosmological entropy profile that gas would achieve with just simple accretion shocks as gas falls into a cluster and heats. So that's a baseline profile below which you wouldn't expect the gas to drop. And in the outskirts of clusters where the cooling times are of order the age of the universe or longer, the gas profiles tend to follow the shape of this baseline profile. Inside the cores of clusters where the cooling time is shorter than the age of the universe, you see some thermodynamic diversity to the cluster profiles, where some clusters have relatively high entropy in the center, meaning very low gas density. Remember, their temperatures don't change by a lot. So the gas density is relatively low here to get this high of gas entropy. And then there's some where the profiles continue to drop and they're have low gas entropy. So they're similar in the outskirts and follow what you'd expect from self-similarity, gas following like dark matter and tracking the process of accretion shocks. But there's another interesting difference in that when the cores have high central entropy, the central galaxy tends to be quiescent and non-star forming. Whereas if the gas in the center has relatively low central entropy, those are the only systems where we find these emission line BCGs, where there's multi-phase gas, there's molecular gas, there's H-alpha gas, there's often star formation signatures, and for many of them, in particular, they have an active and energetic radio source as well. So this bimodality seems to be correlated with the thermodynamic state of the core gas, in the sense that things with low entropy tend to have these brightest cluster galaxies that are on, and the things with high central entropy never have galaxies that are on and have only these red and dead BCGs. And I wanted to give a shout out to Brian's work in his group. His group showed that the pressure, the PDV work that's required to excavate these cavities is correlated with radiative energy losses in the core. This was also shown by Tarazov in 2002 and by Brian's students throughout the years. Somewhat later work, King Cavagnolo with Brian showed that the central galaxy radio sources, the radio power correlates with this cooling radiation that's being compensated for by the central AGN. And so another clue comes from an interesting set of data that was compiled by Gaspari, published in 2019. So the data are plotted here from Gaspari. The lines here are added by myself and Mark Boyd. So the data are on the right-hand side, you have the black hole mass. And on the x-axis, you have the temperature of the gas close into the black hole, well, within a few kiloparsecs of the black hole. And what Massimo Gaspari found was that there is a remarkable correlation between the temperature of the gas around the black hole and the mass of the black hole, even better than the famous velocity dispersion and black hole mass relation. So those are the data points that are plotted. They're the mass of the black hole versus this gas temperature. Over on the left is essentially the energy scale corresponding to the black hole mass times c squared times an efficiency factor of 10.23. So that's 10 to the minus 0.23. So this is this arbitrary but interesting efficiency factor that converts to an energy, that allows us to convert this black hole mass scale to energy scale. And that is thought to be approximately the efficiency is the efficiency with which as the black hole is forming, some fraction of the energy of the mass that's accreted is turned into energy and is lost during the accretion process, either with jets or winds or radiative power. And this efficiency is not well modeled from first principles, but it's a factor that can be put into these AGN feedback models that can help allows people to parameterize the energy available from the process of accretion onto black holes. So, and then on the top axis is plotted the corresponding halo mass out to R200 for systems with the corresponding temperature here, plotted down here. So the right-hand plot is the data, left-hand plot is the corresponding energy scale. The bottom is the temperature of the gas near the galaxy that hosts the black hole, and the top is the corresponding halo mass corresponding to that temperature. So there's an MT relation that translates the bottom to the top. Now, what's the significance of these various lines? The blue line is the energy that's required to lift the CGM by about a factor of 2. So this is the energy of lifting. And kind of the cool thing is this line passes through the data, and it suggests that the black hole mass is somehow tuned to the energy required to lift the CGM by about a factor of 2. So it suggests that lifting is part of the process of quenching both the further stellar growth of the halo, but also the growth of the black hole. We can also put on this plot the energy that is available from supernova from the central galaxy. So if it was at 100% efficiency, it would follow this top pink line. If it was at 10% efficiency, that is the energy from the supernova has a 10% efficiency of coupling to the gas, it would follow this bottom pink line. So supernova really are insufficient to explain what's going on. If we took all of the supernova in the whole halo, not just in the central galaxy, but in the satellite galaxies, you'd get this dashed line up through this region, and it still falls short of the energy implied available to the black hole. The cooling, the radiative energy, that is the X-ray luminosity times the Hubble time. So the total amount of X-ray energy radiated over the history of the universe is plotted in the on this orange dashed line. And so the energy that the black hole releases at a 10 to the minus 2.3 efficiency, it well exceeds the radiative losses of the gas over the history of time, but is well tuned to the amount of energy required to lift the gas by about a factor of 2. This is rather similar to a model that was described by Booth and Shea in 2010 and 2011. They find that with a simple simulation, they get this result with that the mass that's inferred to come out of an AGN or a supermassive black hole as it's accreted is well matched to the amount of energy required to lift the CGM by about a factor of 2 or so. And that is a result that is independent of that actual efficiency. So if you're intrigued by this result, I encourage you to go back to Booth and Shea and check out an independent a version of this conclusion. So I am out of time. So I did plan to stop there, but I had a couple extra things I was going to show if I had extra time, but I didn't think I was going to. So I was correct. And I will just scoot on to the end then. Okay, and so I just wanted to put up a little list of some of the things we're working on at MSU and open it up for questions.
Thanks, Megan. Thanks for a very nice talk.